Okay, so welcome to Bio 3.1 tutorial. Okay, so today's coverage will be carbohydrates. Today we'll cover carbohydrates. So make sure to leave a comment on the comment section so that we can know how best we can attend to you in situations where you are not clear about a particular concept or a question. Okay, so remember for you to see an improved quality of the video, you can always go to your settings and make a few changes so that it is actually clear. Alright, that being said, my name is Chileshe Malimba. I'll be taking you through tutorial sheet number 3 for carbohydrates. Next week on Wednesday and Friday, we'll have another tutorial sheet, one on on proteins, and the other one will be on nucleic acids. Then your last tutorial sheet will be on transcription and translation. Alright, so we'll get right to it. So tutorial sheet number 1. Tutorial sheet number 1, the first question says, define isomerism in detail. Okay. Alright, so what is isomerism? Isomerism is simply a phenomenon, or rather, when we talk about isomers, we are talking about compounds that have the same molecular formula but have different structural formulas. Those are what we call structural isomers. Then we also have stereoisomers. Stereoisomers are simply in the case of carbohydrates, we are saying these are carbohydrates that have the same molecular formula but different arrangement of elements or other atoms in space. Now, I'll take you back to what you did in your grade 12 so that you can just really understand what isomerism is. When we look at isomerism, we are going to cover it under carbohydrates as well as under proteins. So now, in your secondary school, you covered compounds like pentane. Okay, you covered compounds like pentane when you were covering organic compounds. Now, when they were introducing the concept of isomerism, they gave you this as an example. Okay. So they gave you this as an example. This is your isopentane. Now your isopentane, you can clearly see that this pentane and the isopentane have the same molecular formula but different. The arrangement of these guys is different. Then you also have the isopentane. Okay, so these were the examples of isomers. This is your neopentane. Now, in carbohydrates, we also have isomers, which we'll cover in a few minutes. Now, by definition, carbohydrates are simply sugars, or rather hydrocarbons that are made up of carbon, hydrogen, and oxygen. These carbohydrates are energy-rich compounds that most organisms utilize for energy. Some common examples of carbohydrates are the famous glucose, we've got sucrose, we've got cellulose, we've got starch, and I'm sure during grade 12 you covered tests for starch and all the other different types of starch. Now in here we'll try to talk about starch and all these other carbohydrates in details. Now, within these carbohydrates, there are what we call monosaccharides. We've got disaccharides, oligosaccharides, and polysaccharides. So these are the different types of carbohydrates. Now within these groups there are different examples that we can actually look at. Now by definition, monosaccharides, these are actually single sugars that are usually simple. Some common examples are the famous hexoses and pentoses. So to be more precise, when you look at glucose, you look at fructose, these are examples of monosaccharides because these are single sugars. By characteristic, these are usually linear and unbranched. Some of these can be in ring form, but usually they just form single rings, as you will see when we cover question 2. Now, disaccharides, on the other hand, are different from monosaccharides. Disaccharides, these are sugars that are made up of 2 monosaccharides. So, in terms of disaccharides, when 2 monosaccharides are joined together through a condensation reaction where water is actually given out, we call that a disaccharide. Some common examples is your sucrose. Alright, we have sucrose, we have maltose. On monosaccharide we said glucose, galactose. Alright, then we also have fructose. Alright, these are some examples. So when we look at disaccharides, they've got 2 monomer units. In the case of maltose, we've got when two glucose residues or 2 glucose monomers are joined together to form a glycosidic bond via the process of condensation, we see that maltose is actually generated. Then when we look at your common table sugar, the sugar that you use, which is sucrose, is actually made up of glucose and fructose. So we see all these disaccharides. And when we talk about oligosaccharides are a different class of carbohydrates. Oligosaccharides these are actually, by classification, they can also be classified as polysaccharides because these are actually made up of 2 to 10 monomer units. All right. So that's where the confusion comes in when it comes to differentiating oligosaccharides and polysaccharides. However, polysaccharides are made up of 3 monomer units, 3 or more monomer units. These can either be 3, 12, 20, 25, maybe even as many as 50 and more. So some common examples of polysaccharides, we've got cellulose, then we've got starch, we've got glycogen. Of course, for starch, we know we've got amylose and amylopectin, which I will cover in a few minutes. So these are the different types of carbohydrates. Now, question one talks about discussing what isomerism is, and to give some common examples of isomers. So within isomers, we've got two different types of isomers. We've got structural isomers. So in some literature, structural isomers are actually called constitutional isomers. So we've got structural isomers which have the same molecular formula but different structures. Then we also have what we call stereoisomers. Stereoisomers have got the same molecular formula and same structure, but they've got a different arrangement of groups in space. Or rather, the atoms within this, when you talk about the linkages, the bond linkages, they are basically the same, but the arrangement of groups, which I'll show you in a minute. Remember, this course is cells and biomolecules, meaning that you need to know the structure, the definitions, as well as the function of these carbohydrates. So now, some common examples of structural isomers. We've got glucose. Glucose, when you look at glucose, the structure. Remember, when glucose is in solution form, glucose can either be in an open chain form or a ring structure. Should you be asked questions of glucose being in solution? Glucose, when it's in solution, it's always in a ring conformation. All right. So we have an example. This is your glucose. Remember, know the structures. Know the structures of these molecules, because if you do not know the structures of these molecules, you may not know which one is its stereoisomer or which one is its structural isomer. Okay, so this is an example of a structural isomer for glucose. So fructose is a structural isomer of glucose. Okay, so this is your glucose. This is your fructose. So by definition, we are saying structural isomers. These are compounds that have the same chemical. These have the same molecular formula, but different structures. So to prove to you that these are actually structural isomers, you can count your number of carbon atoms. This is your first carbon, which is also your anomeric carbon. This is your second carbon, your third carbon, your fourth carbon, your fifth carbon, and your sixth carbon. In the likewise manner, your fructose has got, this is your first carbon, your second carbon, third carbon, fourth carbon, fifth carbon, and sixth carbon. So they've got, you look at the molecular formula, is the same. They have got six carbon atoms in their structure. 6 carbon atoms in terms of molecular formula, but the structure is same. This has got 6 ring structure. This one has a 5 ring structure. So these two are structural isomers. All right. That being said, we can now look at some stereoisomers of glucose. Okay. Okay, so now these are some examples of the stereoisomers of glucose. This is your glucose. This is your galactose. So now, this is your alpha D glucose. This is your beta D glucose. So these are examples of stereoisomers for glucose. So your glucose, when you look at this particular glucose, you can look at the hydroxyl group. The hydroxyl group on carbon number 1 is on the bottom, but here the hydroxyl group is on top. When you look at the structure, it's the same, but the arrangement of these hydroxyl group is different. For the beta glucose, the hydroxyl group is actually on top, on carbon number 1, right? But on the alpha glucose, your hydroxyl group is on the bottom side of the glucose. So this makes this makes your beta D glucose an isomer of your alpha D glucose. The other isomer of glucose is galactose. You can see on carbon number 4 that the hydroxyl group is on top, whereas on carbon number 4 of your alpha D glucose, the hydroxyl group is actually on the bottom side. So these are some examples of stereoisomers of glucose. Okay, we move on to question number 2. Okay, so question number 2 reads, mention the isomers of glucose and explain what kind of isomers they are. I'm sure we've already covered these isomers of glucose when we talked about the two structural isomers, which is glucose and fructose, whereas we have galactose and your alpha and beta D glucose being stereoisomers because of the arrangement of these atoms and the spatial arrangement. Okay, so question 3 reads, what is the difference between hexose and pentose? What is the difference between hexoses and pentoses? So when you look at hexoses are a class of simple sugars that have got 6 carbon atoms in their molecular structure. So these hexoses have got 6 carbon atoms in their molecular structure, whereas pentose sugars have got 5 carbon atoms in their molecular structure. Okay, a good example of a pentose sugar is glucose. Okay, whereas a good example of a pentose sugar is ribose. Now, I'm going to show you the structure of ribose, a ribose sugar. So remember, pentoses have got 5 carbon atoms in their structure, whereas hexoses have got 6 carbon atoms in their molecular structure. So you can see that this is 1, 2, 3, 4, 5. This is your ribose sugar. This is an example of a pentose sugar, whereas this is your hexose sugar, glucose, right? So this is your hexose sugar. An example is glucose, whereas this is your pentose sugar, ribose. We've got a ribose sugar and a deoxyribose, which is deficient of an oxygen atom on carbon number 2. Alright, so we go to the next question. Question 5. Now, question 5, I'm sure we'll cover where riboses are found and glucose. So, when we look at ribose sugar and deoxyribose sugar, these sugars are very important. They are very important they are very important components of nucleic acids. When you talk about deoxyribonucleic acid and ribonucleic acid, which is your RNA and your DNA. So your deoxyribose sugar is important, is an important and a vital component. We can call it a key component in the deoxyribonucleic acid DNA, whereas your ribose sugar is a key component in your ribonucleic acid, which is your RNA. Now, question number 5, we can go on to question number 5. Question number 5 of the tutorial sheet. Question number 5 says, define a functional group and define the functional groups of sugars, or rather carbohydrates. So now, functional groups, these are substituents, or rather moieties, within a particular compound, in this case a particular hydrocarbon, which is carbohydrates. So with respect to carbohydrates, functional groups, these are just basically moieties, or rather groups within the carbohydrates that are responsible for the chemical properties of carbohydrates. So when you look at these functional groups, they are basically responsible for majority, if not all, the chemical reactions that these carbohydrates undergo. So now, carbohydrates, the functional groups for carbohydrates are actually carbonyl groups. Carbonyl groups. Now, these carbonyl groups are largely made up, they're just made up of your aldehyde and your ketone. Okay? I'm sure you covered ketoses and aldoses. So these are the functional groups, meaning majority of the chemical reactions that all carbohydrates undergo are all hinged on these groups. Okay? All right. So in the case of fats, we covered the functional groups. These biomolecules, each of them, most of them have their functional group. Okay, so the functional group for carbohydrates, remember, is the carbonyl groups, which are made up of the aldehyde and the ketone group. Question number 6. Question number 6 reads, describe the structure and functional difference between monosaccharides and disaccharides. Describe the structure and functional differences. So what this question is asking from you as a student is to talk about the structure of monosaccharides and the structure of disaccharides. So monosaccharides, as I said earlier, monosaccharides are single sugars that are usually linear and unbranched. In some cases, this can form a ring, but in the cases where they are in ring form, they usually exist as single rings. Okay, so in terms of structure, we have a good example of a monosaccharide is your glucose, which I have already talked about. It is also important to know that the body utilizes glucose as a form of energy. So these are energy-rich hydrocarbons. This is your glucose. This is your glucose. Okay, that's your this is your glucose. This is an example of a monosaccharide. An example of a disaccharide, let's take for instance your normal table sugar, your sucrose. Your sucrose is a disaccharide. So this is your sucrose. Your sucrose is made up of two monosaccharides. By function, monosaccharides function as monomer units for disaccharides. Remember, the preferred form of carbohydrates for the body of most organisms, including human beings, is glucose. So when glucose is in excess, the body converts this glucose into other storage forms, such as sucrose and glycogen, okay, as a storage form. So by function, the monosaccharides are usually used for energy because these monosaccharides are energy rich. They are energy rich molecules. So what the body does is that it breaks down these monosaccharides to liberate energy that it needs it breaks them down to liberate energy needed for metabolism. Whereas mostly the disaccharides are a form of energy storage. When the body has enough of these, it usually converts them to glycogen, which is usually a polysaccharide. But in terms of difference, these ones are readily used in the cell, whereas these are usually storage forms of carbohydrates. Now, these monosaccharides are simple; they are linear. Disaccharides are also linear and may have two ring structures. Okay. That being said, the function for these disaccharides is usually to store energy. Now what the body does is it breaks down these sugars into monomer units. When the body breaks down such disaccharides, maybe even other organisms break down these disaccharides, they liberate energy. So these, in comparison between monosaccharides and disaccharides have more energy than monosaccharides. So for each glycosidic bond that is broken down by an organism, energy is liberated and used by the organism. So these have lower energy, whereas disaccharides have higher energy. Alright, we can go to question number 7. Question number 7 reads, illustrate the process of condensation and dehydration using a non-chemical reaction. Okay. By definition, condensation is a chemical process, and when we are talking with respect to carbohydrates, this is a chemical process in which two or more monomer units, which are monosaccharides, are joined together to form glycosidic bonds where water is liberated. That's why we actually call it dehydration, because water is expelled during this joining. Because these monosaccharides are usually monomer units for disaccharides and polysaccharides. So condensation reaction is basically the process in which these disaccharides and polysaccharides are generated, where they are joined together to form glycosidic linkages, or rather glycosidic bonds, and water is expelled out of the process. So a good example is during the formation of maltose. Now you all know that maltose is a disaccharide, meaning it has got two monosaccharides. It is a disaccharide of glucose joining together with glucose to form maltose. Okay. This is actually reversible because it can be broken down. Okay. So when two glucose monomers are joined together through a condensation reaction, maltose is generated. Now I'm going to illustrate. Whenever a question asks you to illustrate, mostly they want you to actually not just explain what's taking place, but to also show them in terms of structure. All right, so I'm going to illustrate how this maltose is generated, which is a disaccharide, through a condensation reaction. So now we have got two glucose residues, or rather two monomers. This is your glucose. Okay, so what actually happens is that when this glucose and this glucose undergo a condensation reaction, when two glucose monomers undergo a condensation reaction, what actually happens is that a water molecule is liberated, or rather expelled out of the reaction. That's why we are calling it dehydration, meaning water is lost. Okay, so what will happen is that this, remember, this is your carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So what will happen is, during this condensation reaction, a 1,4 glycosidic bond will be generated between carbon 1 and carbon 2. This is an anomeric carbon because it is a carbon that is attached to the functional group. So between the anomeric carbon and the carbon that is not actually anomeric, this carbon is not anomeric because it is not attached to the functional group. So what happens is that these two create, or rather generate, a glycosidic bond and form a disaccharide. I hope my diagrams are clear. So this is your maltose, and this is your condensation reaction. So water is actually expelled out of the system. So that's how you illustrate how a condensation reaction takes place in the formation of disaccharides. In a situation where more than one residue is involved, you can generate a polysaccharide, and these polysaccharides in a case where another glucose residue is added, if another glucose residue was to be added, in a situation where another glucose residue is added, you would have another water molecule expelled, meaning you will have another glycosidic linkage where you have a polysaccharide. So remember, in the case of polysaccharide, you can illustrate the formation of a polysaccharide by simply putting N here, where N can be any number of glucose residues. N can be 18, can be 20, can be 50. That's how you illustrate condensation reaction when it is asking you to actually talk about formation of polysaccharides. But in the case where disaccharide formation is involved, just two residues are enough. Okay, I hope that one is clear. Alright, we can go to the next question. Question number 8. Question number 8. Today I'm a bit slow so that you can actually understand the entire tutorial sheet. Okay. Question number 7 reads, question number 8. Question number 7 we've already answered it. Question number 8 is saying, explain why glucose is soluble in water and why cellulose microfibrils are insoluble in water. Now, you remember in your lectures you covered monosaccharides and disaccharides. Now, glucose is a monosaccharide. Cellulose is a polysaccharide, meaning it is made up of more than one monomer. Right? Now, by structure, glucose that's the structure of glucose in solution. It's in its ring form. Cellulose, glucose has got so many hydroxyl groups that are exposed. You look at this hydroxyl group, this hydroxyl group, this hydroxyl group, this hydroxyl group. There's also that hydroxyl group. Because glucose has so many hydroxyl groups, it's easy for glucose to actually dissolve. It is easy. That's what accounts for the solubility of glucose. But when you look at cellulose is a complex polysaccharide, and its molecular weight is so high. It is big because it's a polysaccharide. Now because this guy has got so many hydroxyl groups that are exposed, and the hydroxyl groups, they've got some lone pair electrons and all that. So it's easy for it to actually dissolve. But for cellulose, it actually has a crystalline structure. And due to the crystalline structure, this makes it difficult for cellulose to actually dissolve in water. When you look at its molecular weight and its crystalline structure, it makes it difficult for cellulose to actually dissolve and be soluble in water. So because of the crystalline structure, its molecular weight, it makes it difficult for cellulose to absorb water, or rather to be soluble in water. One important thing as you are taking the cells and biomolecules course, you need to know the differences between glycogen, because these are polysaccharides. Glycogen, starch, and cellulose. Remember, these glucose, most of the drinks that you people take, when you look at carbohydrates, these are sweet. Mostly the disaccharides, they've got a sweet taste. So now, what actually happens is that all these drinks that you usually take up, most disaccharides are used as what? As sweeteners. Now, on the other hand, when you look at polysaccharides, you need to know the difference between glycogen, the difference between starch, and the difference between cellulose. By definition, glycogen is a storage polysaccharide, meaning it's made up of more than one monomeric unit, which is the monosaccharide. Then starch is also a storage polysaccharide. What I mean by storage polysaccharide is that these polysaccharides function as storage units, or rather they function as storage for the monomer units which can be used by numerous organisms. So now, in terms of glycogen, especially in the human body, glycogen is the preferred form of storage for the glucose. Then when you look at starch, it's also important to know that there are two types of starch. There's amylose and amylopectin. Okay, then you can also look at your cellulose. Okay, so your cellulose, for your glycogen, when you look at the difference between amylose and amylopectin, amylose this is a form of starch which is usually, let me not say usually, which is linear and has 1,4 glycosidic bonds. This one has got 1,4 glycosidic bonds. But amylopectin, on the other hand, is branched. It's not linear, it's branched, because it has got your alpha 1, it has got your 1,4 glycosidic bonds and 1,6 glycosidic bonds. Alright. Cellulose, on the other hand, has 1,4 glycosidic bonds. So this one is also linear. But in terms of, when you look at the functional difference, the functional difference is that the cellulose is a structural polysaccharide, because it's usually found in plants, and human beings cannot digest the cellulose because they don't have the enzyme cellulase, which is used to digest cellulose. So most of the times when you are advised by your nutritionist to take some fiber, some vegetables, the reason is because it's gonna go and clean your intestines and your stomach, right? Because it cannot actually be digested. So now, when you look at cellulose, it's a structure it's usually found in the cell walls of plants, whereas starch has got the amylose and amylopectin. Okay, so glycogen also has 1,4 glycosidic bonds. I thought of talking about that one because it's very important for this course. So question number Question number 9 says, explain how cellulose differs from starch and glycogen. Okay, I think I've explained much about this. When you look at glycogen, it actually has a molar mass of 666.5777 grams per mole. So you can easily see that this molecule of carbohydrate is very large. Okay, so you can differentiate these three based on function and structure. When you look at the structure of cellulose, cellulose is actually linear, whereas starch, when you're talking about amylopectin or amylopectin, this is branched. So in terms of branching, amylopectin is branched, whereas cellulose is not branched. Glycogen, likewise, is not branched. So that's a common difference. Then you can also differentiate them based on function. So this one is used to provide structure in cell walls, because cell walls are largely made up of cellulose for the plants, whereas for starch and these are storage carbohydrates. That one is a structural carbohydrate. This one is used to store energy-rich monomers such as glucose as well as this guy. All right, I think that's those are some of the major differences between those two. You can also talk about solubility. This one is insoluble, it's largely insoluble in water. It has difficulties dissolving in water, whereas these two it can readily dissolve. This is because this one, as I said earlier, has a crystalline structure and its molecular weight. All right. Question number 10. Question number 10 says, with examples, explain the important roles of carbohydrates in living organisms. So, when you look at carbohydrates, because we are talking about the function of these carbohydrates in living organisms. So these carbohydrates, when they ask you to such a question, the question is broad, meaning for carbohydrates you can talk about the function of monosaccharides, you can talk about the function of disaccharides, you can talk about the function of polysaccharides to human beings. Now remember, the first important The first important function of these carbohydrates is to provide energy. So these provide energy, whether polysaccharides, monosaccharides, these provide energy. Because remember, we said these are actually fuel for the cells. So the other function is they also prevent degradation of skeletal muscles. So these prevent degradation of skeletal muscles and other tissues. Those, especially those that are found in kidneys, the liver, and the heart. But why skeletal? Let's just stick to that. Say, let's not go so much in detail. Let's just say prevention. They prevent degradation of skeletal muscles. So these carbohydrates also help with fat metabolism. So they also help in fat metabolism. Okay. They help in fat metabolism, meaning if the body has enough energy for immediate use. Remember, the preferred form of energy in these cells is usually glucose. So when the body has enough glucose, it will spare the fat. It will also spare the proteins. Okay, so there are many reasons. So some carbohydrates, as I said, they help clear the gut and prevent constipation. I talked about cellulose, right? Some help clear the gut and prevent constipation. Okay. They also play major roles in cellular recognition. Okay, so these play major roles in cellular recognition. So these also have, they are vast in terms of function. There are a lot of functions that we can actually look at. So we also have some of these form components. Some of these carbohydrates, they form components of biomolecules. You talk about DNA. It has got ribose sugars, right? So without the ribose sugar, there would be no DNA. And you know how important DNA is to life. When you talk about if there were no carbohydrates, there would be no RNA. And you know how RNA is important. We'll cover that when we come to genetics and molecular biology course. So they are also part of cells. These make, we talk about glycoproteins, these are part of cells. They make components of cells. So, and they are very important in the functioning of cells. All right. So we can go to the last question, which is question number 11. So question number 11 reads, discuss in details the reactions involved in the chemical test for the presence of carbohydrates in a food sample. Okay, I'm quite certain you covered this one in a lab with Mr. Munalola when you covered the test for carbohydrates. the test for reducing sugars, the test for non-reducing sugars. You cover this. Okay. In a case where we have a particular sugar, CH2OH, I'm gonna use the Fisher projections. Okay. This is an example of a carbohydrate. So what happens, remember, when you're doing the test for carbohydrates, you use the Benedict's reagent. So what the Benedict's reagent does is simply alter the color of our carbohydrates. So the copper 2 ions are responsible for the color changes. Hydroxy. So what the copper 2 ions in the Benedict solution does is it gives you a red precipitate, thereby indicating the presence of sugars. So what it does is it basically just plays around with the structure of these carbohydrates, and the action of the copper 2 ions in the Benedict's reagent actually play around. When they play around, they undergo reactions whereby a red precipitate is observed, thereby indicating the presence of these carbohydrates. Alright, that being said, that was the last question on tutorial sheet number 3 on carbohydrates. It is of utmost importance that you understand the structure of these carbohydrates. In summary, it is of utmost importance that you understand the structures of these carbohydrates as well as the function in living systems, because the cause cells and biomolecules basically hinges on the structure of these biomolecules, their function in cells as well as in the world out there. So make sure you know your structures, make sure you know your definitions and the function for all these biomolecules. So next week, Wednesday, we'll be covering the tutorial sheet on proteins. We'll be covering tutorial sheet on proteins next week on Wednesday. 11 hours to 12 hours. That being said, I wish you all the best. See you next week.